Hello, Intro to Stats. We are going to take some notes on 5.5 today. I do want to point out just right at the beginning of this video that you do not necessarily have to watch these notes. You could just take the notes from the book, page 365 through page 371. However, if you would rather listen to my voice, which I know is so absolutely soothing, you could definitely listen along. All right, so 5.5, we're going to skip. So we took some notes at the beginning of this chapter, and we're actually going to skip over some of that middle stuff, and we're going to talk about some continuous random variables. So what you have in front of you, and this is actually the same example as in the book, is a relative frequency histogram of the scores of the 7th grade students in Gary, Indiana on the Iowa Basics test. I don't know about you, but we did these when I was in grade school, and it was like the best week of school because even though you had testing all day, you did not have homework. So that was lovely. Anyway, let's talk about this distribution a little bit. What do we notice about its shape? What about where's the center? How spread out is it? And are there any outliers? Remember our socks: shape, outlier, center, and spread. I would say looking at this, our shape is relatively symmetric. It has no outliers. It doesn't look like any outliers. No outliers. Its center, I would say, is centered around 7. And spread, it's kind of hard to say, but we could say the range is from maybe like 11.8-ish to 2, so that would be 9.8-ish. Not really, they didn't ask us to do this, but just good to notice. Okay. It also says the scores are grade level equivalents, meaning a score of 6.3 indicates a student's performance is typical for a student 3 months into grade 6. Kind of cool. If we look at this, hopefully we notice that this is a continuous random variable. So let's say X is a student's score on the Iowa Basics test. And we just said this, but it is a continuous random variable. Why? Well, because I could get a score of 6.3, or I could get a score of a 9.1, or anything in between what looks like 2, our lower end, and a little bit under 12, our upper end. All right, this is great and helpful, but what if we were asked to find something like the probability that x is less than 6, or the probability that some student scores below a 6th grade level? So how would we do that? Well, technically, we would need to find this area right here, how often that's happening and how often it's happening here, and all of this. And while we could do that, we actually, as statisticians, do something. First, we create something called a density curve, and I'm going to draw it on the next slide, actually. All right, so what is a density curve? Well, if we have this distribution right here of our Iowa Basics skills, a density curve is a smooth curve that gets drawn on top of this distribution kind of to model the data. So this is not going to be great because I'm doing this on the tablet, so please forgive me. But if I take my marker and kind of make a smooth curve that generally estimates the shape, I have created a density curve. Let's talk about what this density curve actually is. So it's got a couple things that we want to mention. A probability distribution of a continuous random variable is described by a density curve, again this blue thing right here, or a curve that has 2 characteristics. One is always on or above the horizontal axis. Not gonna lie to you guys, this is a true statement, but it's not really that important right this moment. But the important thing that we need to understand is that it has an area of exactly 1 under it. Okay, so let's think about what that means. If this is my density curve, and it is a density curve for, let's just do the same example, our Iowa Basics, and I find the entire area under it, or all of this shaded region, if I find this area, What I'm really finding is the probability that a student gets between a score of a 2 and we'll say 12, because let's just pretend there's someone like right here. Well, what are the chances a student gets between a 2 and a 12? Those are the only scores they got. That is all of our data, or there's a 100% chance, a probability of 1, that a student gets this. Well, why is this helpful for us? It's especially helpful because we can use density curves to find probabilities. Let's say I still have this same example, the Iowa Basics, and let's say I want to find that probability from above, or the probability that a student gets less than a 6 on the exam. Well, then I'm looking for this shaded area right here. And in this section, we're not actually going to talk about how we find that with a curve that looks like this. If our density curve is something, I think you'll see this on the homework. A density curve is something where you know the shape, right? I can find the area of a rectangle. Then we're able to find this shaded region because it's something we know. Right now, we don't necessarily know how to find this, and that's okay. We're just going to be drawing it out. Let's talk about a couple other things. So mean and median of a continuous random variable. I'm going to draw 3 drawings for you. I'm going to draw a curve that looks like this. We're going to say it's symmetric. I'm going to draw a curve that looks like this. This is skewed. Which way? Which way would you want to go skiing? This is skewed to the right. And we'll draw one more. Probably not surprising. It's going to be skewed left. And one thing we're often asked is to find where the mean and the median are in any given distribution. So the mean of our distribution is often thought of as the balancing point. So if I were to take this thing and balance it, where would it balance? Now, the mean of a symmetric distribution is pretty easy because it's just right in the middle, right? This left half weighs the same if we're pretending it's a physical object as this half. But what about distributions that are skewed? There's a lot of area over here and less on the right side. But this right side is pulling the mean in that direction. If I made the mean right here, which is incorrect, I'm just going to say, and I found this area, well, look at how much bigger this is over here on this right side. All right, so I know that that spot that I just put is not where my mean is. So where's the mean of a skewed right distribution? It's more towards that tail. This over here is our mean. And then similarly, a skewed left distribution, the mean is going to be more towards that left tail. Here, I maybe didn't draw it perfect, but actually I'm probably going to scoot it over just a little bit. If I found this area and this area right here, they should be about equal in weight. If I talk about the median of a distribution, the median is the middle point, or the point that has exactly the same amount on the left and the right. Our median and mean of a symmetric distribution are exactly the same. A median in a skewed distribution is going to be more towards this middle region. So here's our median. Why? Because, well, we've got all of these things bunched up here and all of these spread out. The same number has to be on either side there. Last thing I want to talk about is something called a normal distribution, which we've actually seen now twice in my little drawings. But a normal distribution, or let's go for the definition first and then we will draw one out, have the same overall shape. They are symmetric, they are single-peaked, and they are bell-shaped. Okay, that sounds familiar. We just drew a symmetric distribution that was single-peaked, had one mound, and has this general bell shape. Okay, so this is a normal distribution right here, what I just drew. In a normal distribution, the mean is exactly the same as the midpoint. This is the symbol mu, and it stands for the mean of a normal distribution. It is also the same as our median, because if I am symmetric, my balancing point and my middle are going to be exactly the same. And then the other piece of this is that a normal distribution has sigma. This is sigma right here, which stands for the standard deviation, and it measures the variability or the width of this distribution. I think a long time ago, when we were actually still in school, we talked a little bit about the difference in our standard deviations, or what it meant for a variable to have either like a big standard deviation or a small standard deviation. Oh boy. I'm going to draw two different normal curves here. And if I look at these, this distribution right here has a much bigger spread. It is wider than this little guy over here, which means this standard deviation of, let's say this is distribution A and this is distribution B. So standard deviation of A is less than the standard deviation of B. Standard deviation is telling us how spread out it is. And the other really cool thing about a normal distribution, okay, that wasn't perfect, but it always is centered around this mean. And then we kind of have these 1, 2, 3 marks above, 1, 2, 3 marks below. Each distance here is a standard deviation. So this point, oops, I'm going to move this. Hold on one moment. Okay. All right, so the mean is the center, and the standard deviation is how spread out this thing is. And I was just saying that this point then would be whatever the mean is plus 1 standard deviation. This point is whatever the mean is plus 2 standard deviations. This point is our mean plus 3 standard deviations. And I could do the same on the left side. I'm not going to write that if that's okay. But the mean minus 1, the mean minus 2, the mean minus 3. Why is this something we need to know? Well, let's do one example together. Many studies on automobile safety suggests that when a driver of cars need to make emergency stops, the stopping distance follows an approximately normal distribution. Okay, approximately normal distribution. Suppose that for one pickup truck traveling at 62 miles per hour under typical conditions on dry pavement, the mean stopping distance is 155 feet, and it has a standard deviation of 3 feet. To sketch the probability distribution of x, the stopping distance for a randomly selected emergency stop. Label the mean and the points that are 1, 2, and 3 standard deviations from the mean. All right, so because they told us it is an approximately normal distribution, I get to draw that beautiful bell shape, and I know it's not perfect. I apologize. And I know that the center, the mean, is going to be 155. I also know that there's going to be 1, 2, 3 points above, 1, 2, 3 points below, and now I need to label these. The standard deviation is 3 feet, so this first point would be 158, or 3 above 155. I add 3 again to get 161 and 164. Hopefully I did my algebra right there. If I go below, I'm going to be at 152, 149, and 146. And that, my friends, is the probability distribution of x, or the stopping distance for a randomly selected emergency stop. Reminder, if I were to find the area totally under the curve, it would be 1. But I'm probably not going to be asked to find the entire area. That wouldn't make sense. Likely, we're going to be finding, and this will be our next section, more pieces like this. Just a little bit. What's the probability that you can't really see this, whatever, that it takes me less than 149 feet to stop, or something like that. All right, I hope you have a lovely day, ladies. I miss you, and